The Milky Way has a diameter of 100,000 light-years and contains about 200 billion stars. But what do we really know about our galaxy? Well, it seems we never stop learning, even about what is right on our cosmic doorstep. In fact, over the past few months, specialists have gathered a series of spectacular pieces of information that shed new light on the Milky Way. This has even led to a fundamental shift in our understanding. Recent data suggests that we have been categorizing the Milky Way incorrectly for a long time. But that's not all. Astronomers have also discovered a gigantic structure, 16,000 light-years long, within our own galaxy, and they observed that this strange gravitational monster in the galactic center has gone through something that impressively demonstrates the inherent powers of the universe. To begin with, here's a simple test question. Why is the Milky Way called the Milky Way? Well, if our galactic neighborhood carries the word milk in its name, it is thanks to ancient Greek mythology. According to an old myth, when we look at the starry sky, we see nothing other than the spilled breast milk of the goddess Hera, a milky band that applies not only to our own galaxy but to all cosmic systems. The ancient Greek root galaxia simply means milk. Now, if we move away from ancient mythology to focus on astronomical facts, we recognize that the so-called milk of the gods is actually just clumps of stars scattered with nebulous gas and dust. However, since we are located in the middle of the Milky Way with our planet Earth, it is only natural that this Milky Band, which rises in the southern sky on clear summer nights, does not represent the entire galaxy but only a small portion of it. From our point of view, it is simply not conceivable to see the Milky Way in its entirety. Nevertheless, astronomers have been able to create a general map of our galactic origin. The Milky Way is classified as a barred spiral galaxy with 5 spiral arms, 2 of which we can see in the sky. Additionally, the Milky Way's diameter is estimated to be 100,000 light-years, though its thickness is only about 3,000 light-years, and the thickness of the galactic core mentioned earlier is around 16,000 light-years. The true center of our galaxy remains imperceptible to our eyes due to the many dark clouds that obstruct our view with interstellar matter. Despite these visual barriers, it is now considered certain that a growing monster resides at the heart of the Milky Way. After all, Sagittarius A*, a supermassive black hole, holds the mass of about 4 million suns. Contrary to what you might think, this is not a special case for galaxies but rather the rule. In fact, specialists now assume that nearly every galaxy is adorned with such a supermassive gravitational monster. As for stellar black holes, which are much smaller and result from the collapse of stars, specialists estimate there are about 100 million of these strange objects in the Milky Way. When it comes to the number of stars, estimates vary widely. While some believe our galaxy has only 100 billion stars, others suspect it may contain as many as 400 billion celestial bodies, all shining brightly. Given that data from the Kepler mission and other studies suggest that there is, on average, 1 or 2 planets per star, there could be anywhere between 100 and 800 billion planetary worlds in the Milky Way. However, not all these planets resemble a cosmic twin of Earth, which is quite obvious. Yet in 2022, researchers from Nottingham determined that as many as 36 advanced civilizations might have developed within our galactic home system. The Milky Way is not a solitary galaxy. In fact, it is part of a much larger and broader structure. On the one hand, the Milky Way belongs to the Local Group, a galaxy cluster containing about 35 members. On the other hand, the Local Group itself is part of the Virgo supercluster, a massive galaxy supercluster, which is in turn part of the Ionia Chaos supercluster. In other words, the Local Group, including the Milky Way, is under the influence of the enormous Ionia Chaos supercluster, or at least it was according to previous models. A new map of the gravitational attraction zone in the nearby universe now suggests that we have been mistaken about our galactic affiliation. It turns out the Milky Way does not belong to the Ionia Chaos supercluster but to the much larger Sanctuary supercluster. These attractors act like gravitational wells, drawing galaxies toward them over vast regions, much like the shape of a riverbed determines the flow of water. The study that previously attributed the Local Group to the Ionia Chaos supercluster was based on 8,000 galaxies, but the new study, which utilized data from the Grand Streams 4 study, includes 56,000 galaxies in a region about 1 billion light-years in diameter. This new, Much larger dataset has revealed that a total of 17 massive gravitational wells exist in our cosmic neighborhood, and the movements of structures associated with the Milky Way prefer to move toward the sanctuary supercluster. In numerical terms, this means that nearly 60% of the structures are flowing toward the sanctuary supercluster, while only 40% are heading toward the Laniakea supercluster. Overall, this discovery offers astronomers new perspectives on the gravitational landscape of our nearby universe. But the newly identified phenomenon located at the ends of the Milky Way's bar is also completely new. Indeed, we now know that gigantic magnetic structures, more than 16,000 light-years long, originate there, rising above and below the plane of the galaxy. Elsewhere, the particular origin of these magnetic fibers also provides a crucial clue about their cause. Since they do not originate from the galactic center but rather from the outer regions of the star-forming zone, scientists suspect that they result from the collective effect of overlapping stellar explosions. These stellar blasts can eject material at speeds of up to 1,000 kilometers per second, creating galactic winds. Additionally, these stellar explosions might be responsible not only for the magnetic fibers, but also for powerful radio structures extending well beyond the disk of our original galaxy. The collision of giants, such as the Sagittarius A** black hole, with another black hole may have contributed to this chaotic environment. While a supermassive black hole resides at the heart of the Milky Way, as mentioned earlier, it is not considered an active quasar. Quasars are extremely energetic galactic cores that emit enormous amounts of energy, often surpassing all the stars in their galaxy. Sagittarius A** has long since retired from active duty, and today, only gigantic gas bubbles and gamma-ray jets testify to its past activity. However, despite all this inactivity, our supermassive black hole continues to captivate specialists. Data from the Event Horizon Telescope (EHT) has revealed that this massive object spins at an astonishing speed and is also tilted relative to the galactic plane. However, this discovery also raises a significant astronomical problem. If the data are correct, they contradict our models for the growth of supermassive black holes. These models suggest that such giants should remain in the material of their own galaxy and move at roughly the same speed and level as the galaxy itself. To understand why Sagittarius A** behaves differently, researchers have returned to their models, simulating various scenarios based on this data. Their goal was to determine which evolutionary history best explains the observed features. After extensive simulations, an astonishing result emerged. The usual accretion models were insufficient to explain the observed properties. Astronomers concluded that Sagittarius A** must have collided and merged with another massive black hole in the distant past. This reconstruction showed that the partner in the collision had about 25% of the mass of Sagittarius A**, and it was almost certainly a massive object perpendicular, and although the black hole in the active region is 4 times more massive than its homologous counterpart, the combination had a significant influence on the incorporation of the partner. In addition, the smaller partner, which had previously merged with the focus of a dwarf galaxy, radically changed the speed and the orbital alignment of Sagittarius A*. At the same time, the galaxy and the dwarf galaxy moved perpendicularly to the Milky Way and probably rotated in the opposite direction. The data reveals exactly when the merger of the black holes had to have occurred, and it perfectly correlates with the known history of our galaxy's origin. According to these data, the Milky Way collided with the Gaia Enceladus galaxy about 10 billion years ago. In detail, the mass ratio of the galaxies in this case was also 4:1. Moreover, the merger had an inclination of 145 to 180 degrees, standard to our plane of the sky. In other words, the close galactic encounter 10 billion years ago presented exactly the same characteristics that can best explain the behavior of Sagittarius A** today. Ultimately, the two supermassive black holes merged approximately 1,000 billion years after the merger of the galaxies. After the waves of cosmic turmoil had settled, the orbital speed and inclination of Sagittarius A** approached their current values. This exciting discovery is additional proof of the dynamic and primitive events that underlie the current structure of our galaxy. At least in theory. In practice, the merger of supermassive black holes has not been directly observed. However, specialists hope that this will change in the near future. It is at this moment that gravitational wave detectors, such as the Laser Interferometer Space Antenna LISA, will be able to detect and analyze the dance of giants. And if you look below the video, you will see the thumb and the subscribe button. Press the like and subscribe buttons now to never miss a new video from us. See you soon.